right? Well, we know that D is also an element of NP complete, which means that for all D in NP, we get that D is polynomial, D prime in D is polynomial reduced prime to D, but we know that D is an element of P, therefore all of these guys in D prime reduced to D.
So,
This can be solved in polynomial.
so first we assume that D is polynomial.
Right, because that's the first half of this implication.
So that means it's, how does
but we
that
also
mean NP complete?
What? What is that?
So D, okay, so we're proving the forward implication, right? So assume D is polynomial time, but we also know by the first statement, D is an NP complete,
Yeah.
right? So we know that since D is an NP complete, we know that all problems in NP can be reduced to D. But since D is an element of P, then all problems in NP are in polynomial time.
Right.
And therefore, P is equal to NP. Get that? Alright, one more time.
Okay.
We're proving the forward implication. We assume that D is an element of P.
Yeah.
Now we know that D is an element of NP complete because that's given in the question, right? Now we know that because D is an element of NP complete, for all D prime in NP, it can be reduced to D in polynomial time. Now we know that D is in polynomial time, so since all the problems in NP can be no harder than D, then all problems in NP are solvable in polynomial time, hence P is NP.
Oh, because NP complete is also NP hard, so therefore do.
Exactly.
Okay.
Exactly.
Okay.
Or yeah, if you want it to be more specific, NP hard, because that makes more sense, right? The other way, assume this one's an easy one. So if P is equal to NP, so we know that because since D is an element of NP complete, right? We know that D is an element of NP, right? Because by definition, just by definition. So in order for D to be an NP complete, it has to be in both NP and in NP hard. But if D is an NP and P is equal to NP, then this implies that D is in P.
Yeah.
Proof.
Done. Beautiful.
Now we begin the proof.
Now we will
All right, and that is it. One more thing, I guess, before we're done the lecture. So that's the proof of that.
No.
Yo, can we do the last lecture tomorrow? Yo, actually, yeah, bro. Yo, let's do last lecture tomorrow, bro. It's enough. My brain's not working anymore.
Bro, just come here.
You just call and let them know it was a mistake. And you're broke as fuck.
He fucked up impressive. Bro. I started right now. I think you all done it.
I put the order through, you gave me the phone,
Yeah, we
I
sure
put the order
ordered
through,
it.
and it wasn't going through. I guess
200% arguing yes.
Okay, that's it.
The dude bought a what? VR set.
Oh, cook,
We don't.
cook, I'm done.
You want a Turing award for that proof? Okay, last thing to know. So again,
Added it back in.
to find an NP complete problem is very difficult, right? Because we have to prove that all problems in NP reduce down to it, right? So even though we have this nice theorem, proving that a problem is NP complete is pretty still hard because you gotta find every problem in NP and reduce it down to that problem.
Yeah.
But thanks to good old Cook, you prove that SAT, which is what I showed you guys, that given a formula F, given a formula like for example, which is a bunch of Boolean statements, can the inputs be set such that it's true? SAT is NP complete. Okay, proof is too hard for us, so we don't have to know it. But just know that this is an important result, because now that we have one problem in NP complete, first of all, if this is solvable in polynomial time, then we can prove P equals NP. So we have, given that, so now we have at least one problem in NP complete right now. So that's good at least, because then if this is solvable in polynomial time, then we can solve P is equal to NP. But in the next lecture, we can grow our set of NP complete problems without having to actually check that all problems in NP reduce down to that thing, whatever, I don't know. All right, okay.